Swayam Prabha. Digital India. Educated India.
Welcome everyone to the session 2 of end-to-end accelerated uh, deep learning. This particular session would be taken by Dr. Tosin. Tosin is working as a GPU advocate at NVIDIA and is based out in Korea. And over to you, Tosin, for taking the session today.
Thank you, Barack. Hi, everybody. I welcome you to this section, which is based on end-to-end accelerated data learning. And today we will be talking about optimizing deep learning training. And we will focus on automatic mixed precision. So that's what we will focus on today. First of all, I'll be talking about deep learning training optimization. So what do we refer to as deep learning training optimization? So we're talking about optimization algorithm, which is used during the training of a deep neural network in order to achieve a desired goal. And in the nutshell, you are reducing the loss to a minimal level. So this is commonly used when we are training a deep neural network. So these are optimizers that are being used. So these optimizers, they help us to help the deep neural network to be able to reach convergence level faster. And so what is actually being tuned in the deep neural network are the learning rates and the weights. They're the one that are being tuned, and also there are other parameters which are also being tuned, like the batch size also they are being tuned. So an example of optimization algorithm is the gradient descent. So the gradient descent is commonly used, and we have types of gradient descent that are used. So I've listed three here. We have the stochastic gradient descent, which have been used. This stochastic, what it does is that it picks the data in batches in terms of randomly using probability. Also, there is the mini batch gradient descent as well. These pick chunks of the batches, it feed them into the model. And also there is what we call the momentum. So this momentum is used to reduce the high variance in the stochastic gradient descent. There are other examples of optimizer like the Adams, the Adagrad, and Adadata, and many of them have been used, which I know many of us are familiar with this. So in the event where training models are becoming more complex, researchers are trying to solve complex tasks, it requires larger models to be built, and also more data are also required to be used to build these models. So in this light, there's need for what we call the advanced optimization for deep learning training phase. So, and when you want to go through this level, there are things which you might need to consider. So you'll be looking at the memory consumption to accommodate large DNN model. And also you'll be looking at the memory bandwidth also, which will be required to transfer data. And large model might require large data, and there is transfer here and there that will be needed during the training phase. Also, you're looking at the word speed up in terms of computation, and which will require some tensor core. So, and how do you make use of advanced optimization that can give you all these attributes? So, example is what to use GPU. You accelerate with GPU. That's one level of advanced optimization, and another one is the mixed precision, which we are going to focus on today. And there's also an aspect called the XLA, which is Accelerated Linear Algebra. This is from TensorFlow, a special compiler. And also there's the transfer learning. So we'll talk about transfer learning in our subsequent course. So we'll focus first of all on the mixed precision. So what do we refer to as mixed precision? Mixed precision is using different numerical format. With respect to deep learning, we can say mixed precision is the use of single and half precision for computation during the training of deep neural network. And what do we refer to as single precision? Single precision is simply the float 32 is what we refer to as single precision, while half precision is float 16, which we call FP16. So we're looking at a scenario where in the training of a deep neural network, these two precision data type are being used. So it is a high level optimization process. And how for you to use this mixed precision, there are requirements. That is, we look at the resources that the usage of this precision are possible. So you must consider the GPU architecture, which facilitate the use of these mixed precisions. First of all, the one we have here is the Ampere. So it is possible if your GPU is Ampere architecture, you can use mixed precision. It's possible for Volta architecture. Mixed precision is also possible, and also for Turing architecture, mixed precision is also possible. So we would like to talk about Tensor Core. So in those architecture, how is it possible for mixed precision to be used? It is possible based on the Tensor Core that exists in those architecture. So, and what are Tensor Core? These are just dedicated cores for matrix multiplication that goes on in the deep neural network. The deep neural network itself is made up of matrix multiplication and convolution. And this convolution and matrix multiplication, those tasks can be handled by the Tensor Core. So, and we'll be talking about mixed precision. We'll talk about FP32 and FP16. So the Tensor Core, they have data type which are fit into F32, also FP32, FP16, bfloat 16. So we'll be able to see that computation will be much easier because we have cores that are dedicated for that computation. And in doing that, it doesn't require you changing any code. And at the later end, you get maximum speed up with that. We can also look at the IEEE standard for that, which is the 754 IEEE standard. The first one you can see here is that is for FP64. This is for FP 32, then there's the one for FP16, the floating point 16, and there's the bfloat. So why the bfloat? The bfloat comes because there is a dynamic range issue with FP16, which the bfloat is able to overcome that. But however, with those dynamic range issue, using a method called scaling can make our FP16 perform better to overcome that dynamic range issue. So for more, you can check this link. You can get more on that. But I wouldn't want to bother us more into these details because we want to focus on the empirical side of it, which is the practical side. So what are the benefits of mixed precision? The first thing is that with mixed precision, you are able to perform matrix multiplication and convolution operations in your deep neural network with maximum speed up. That is, mass intensity operations are being performed using the Tensor Core. Like I said before, that the tensor core is dedicated for such operation, and also it requires less memory bandwidth. So when it requires less memory bandwidth, then you can transfer more data. Operation can be done. So in a short time. Then it requires lesser memory. Why? Because it requires lesser memory in the sense that operations are being performed in half precision mode. So if those operations are being performed in half precision mode, it requires lesser memory, and thus you can train large models very well. So, and after using mixed precision, so what are the benefits you can also get from there is that you get minimum of 3x speed up based on Volta architecture and also Turing architecture if these are the GPU architecture you used. So based on that, you can get 3x speed up. But if you use Ampere, you will definitely get more than that. There are many, if you want to know the classes of your architecture of your GPU, so you can check online. There are several of them online which you can check on. I think I look up somewhere. So if you check Wikipedia for that, you can see this is a compute capacity here. So you'll be able to know the type of your architecture you use. This is you can see Kelpie, you can see Pascal. We have Volta here, the GPUs that are there, Turing. You can see the classes of the GPU that you use. You also have Ampere here, the classes of GPU that belongs to that. You can have all of that. Then mixed precision in training. So how do you train your model using mixed precision? So ideally, the training with mixed precision will help you to speed up computation because those operations that are performed in half precision format. That is, it's perform those operations using float 16, the FP16, and then the minimal information are being stored in FP32, which is the single precision. So the process is that you are using both FP16 and you are using FP32 as well. So during the training, what are the steps you need to take during the training is that you need to port your model to use the FP16 data type where it is appropriate. The only place you will not use the FP16 is if your model, maybe you're dealing with multi classification attacks where you might want to use softmax activation function. So the softmax activation function, you have to use FP32 there. Then the other part, you will be able to use FP16. And the second step is that you need to add loss scaling to preserve small gradient. So why this is that when you use mixed precision, because of the computation that happens with FP16, it usually leads to small gradients, which is we call it underflow, such that during the gradient computation, the gradient is so small that sometimes it leads to zero value, and those zero values affect the accuracy of the model. So you will not be able to get the accuracy you will get if you are using only FP32. So then the loss of your model has to be scaled. And how do you scale? You scale by multiplying that loss with a particular value. So during FP16 porting in your model, so how will you be able to achieve this? Is that you used frameworks that Tensor Core are enabled because the task is being performed actually by Tensor Core. So because those Tensor Core, they also have precisions, which is based on FP16 and FP32. So you choose FP16 format for your tensor, which helps you to do the matrix multiplication that are there, the convolution operation. Also, it works with a fully connected layer, and also you keep all the hyperparameters of FP32, that is the floating point 32 training section there. Now, like I said earlier, there are issues with this. The issue that will arise here is that FP16 has a way of what we call dynamic range being too narrow. Hence, it leads to what we call the underflow. So gradient become very small that it leads to, well, you might have zero gradient, and this will affect your training. So it requires a gradient. It requires such that you need to shift, do some kind of shifting into FP16 representable range to match the accuracy of FP32 that you have. So now do you achieve that? Is the solution is that you use what we call scaling, and scaling, which we have I've mentioned before, is that you multiply by a particular threshold. You multiply your logs by a particular threshold, and what you get is the resulting is what we call scaling. But I will still explain further as we continue. So FP16 has a dynamic range which is sufficient for you to train, and it does this in a way that it affects the gradient of your deep neural network. And so what you need to do is to do scaling, like I said, but while doing the scaling, there's an issue that do arise as well, because when you scale, you multiply by a particular threshold value, it can result to what we call overflow. And what do we mean by overflow? Overflow in the sense that you will be having values that may lead to infinity or NAND value that will lead there. So that is what happened in that sense. So, and the next phase is loss scaling. So how do you perform loss scaling, and what is the reason for loss scaling? The reason for loss scaling is that you want to preserve this small gradient. How do you preserve it such that you are able to train your model as if you were using FP32 only? So the first thing you do is to what? You make a single multiplication by scaling the loss value. So when you scale the loss value at the forward pass, so what do we mean by forward pass? This is like the forward propagation. That is, when your model first run, your deep neural network, when it runs and it eats the output, before it comes back again, which is what feeding the output it gets, feeding it back to deduct from the weight. So, which is the process of back propagation. So, the first thing, what I'm trying to say is that you multiply your loss scale. For example, if I assign 1024 to my loss as my loss scale, I can compute my model here, get the loss, and then use the loss scale, which is 1004, to multiply and add to the loss. So this is what we call scaling. So this is done at the forward pass of your model when your model initially run the first time. So then you compute the gradient. Secondly, that's what you do. You compute the gradient. So after you compute the gradient, then you unscale back again. You unscale back. So unscale back. So how do you scale back? You divide the gradient which you compute by the value you used to scale initially. So when you do that, then you can now update the weights. So there's a procedure for doing that. This is a simple algorithm to do that. You can see here. So the first line is what? You maintain a primary copy of your weight. Your weight will be in FP32. Then during the iteration, so this iteration, this is what happens while you're training your deep neural network, where you can have the step and the iterations that are there. So within that step and iteration, you can make an F16 copy of your weight. And after then, so that F16 copy of your weight, you perform that with what? With the forward propagation. That is the initial runs. Then, so you scale. So how do you scale? Which I've explained here. You scale, you multiply the resulting loss with a scaling factor X. So the scaling factor X is what you have here. Then you can now do your back propagation. So after the back propagation is performed, then you unscale back. That is, you divide the gradient you get there by the value of the scale, and then you can now proceed to update the weights. So here, how do we know how do we pick a scaling factor? Like, okay, do we just pick 1024 or we just pick 1, we just pick 2? How do you know how to pick that? So there's a process for that. Is that the first one is you can pick a constant value, scaling value, and that can only be done if you have the statistical gradient value for your gradient. If you have the statistics for your gradient, that is when that is possible. Or you can use some brute force method, which you refer to as trial by error, to test if this particular scaling value that you pick, if it will not run into overflow. So you can use trial by error. Now, why do you have to use trial by error? Is because this scaling factor is dependent on some other attributes or factors like your network size, that is your model size, the framework you are using, whether you are using TensorFlow or you are using PyTorch or you are using MNet, also the mini batch, also the size of your mini batch. It also depends on that. So that's why you have to try until you're able to get the right scaling factor for the kind of task you're doing. Then also you can choose a value which will not exceed the maximum value which is representable in FP16. And that maximum value is the 65,400. This value have been proved to be efficient and work well and in research. That it is, if your value is below this range, your scaling value, then your model would definitely do well. But while doing this, you must avoid what we call the overflow. So how do we now train? Because while you are trying to pick that scaling value, you need to test it during your training and see that, okay, this value is scaling well and it's not leading to overflow, or you are not experiencing an underflow there. So the first thing you do, this is an algorithm here, is that you maintain the primary copy of your weight, which is in FP32. So how do you have this? Is that your model variable data type by default will be FP32. Then you initialize your scaling value to a large value. You just pick a large value which is less than the value I mentioned here, which the result will be less than this. So you pick that. Then in your iteration, so you make a copy of your FP16 weights. Then you perform forward propagation with it. Then you scale using with the value. Then after you scale, you perform your model perform the backward propagation. So after the backward propagation is being performed, so what you need to do is what you have to check. You check if that does not result to overflow, that is infinity or none in your weight, your gradient weight. So if that occur, what you need to do is what? You need to reduce the value of that scaling factor X. You reduce it from the initial one, then you will skip the weight update. You wouldn't update because you can't update with an infinity or a non-value in your weight. So you skip that. So when you skip that, after you have reduced, then you start all over again. But if that is not the case, then what you need to do is you unscale back your gradient by dividing it with the scale factor value that you pick, and then you complete your weight update. So when you complete your weight update, then so after that has been successful, you check your model as the iteration fully run. So and if while the iteration fully run, you check that there is no infinity or non-value existing in between the iteration, then you can also increase your scaling value. Since the iteration you have performed, there is no overflow, so you can increase it. So when there is an underflow, when there is an overflow, you reduce it until you're able to get a value where overflow doesn't occur anymore. And that after that value, a slight increase in that value may lead to overflow. So at that exact point, you can use that particular scaling factor. And this is an example here, which is performed on using big LSTM. So what you can see here is that the FP32, the loss, the y-axis is the loss. The loss is the black one. You see the loss decrease it decreased steadily. Then the mixed precision used, when the loss scale is at 1, you can see it's decreased and suddenly rises again. So which doesn't give good lost function. It doesn't give good loss. So because the loss is increasing again, then our accuracy will be down. So when the mixed precision loss is scaled at 128, we can see, which is the green one, it's give the same result as if we were using FP32. So it was able to achieve the same result as FP32. However, they were able to use it to train larger models. It requires less memory, we gain speed up as well. So in summary, the mixed precision training is that you have to choose a floating point of FP16 format. Then you perform your forward pass in your model. After that, you scale the loss, and then do your back propagation of the scaled gradient. And then you unscale back the gradient, and the optimizer performs the weight update. These are just the summary of all what I've been saying. So is there a simpler way with all this more of theoretical scale on scale and do that? I would say yes, there's a simpler way. So the simplest way that is available method is what we call the automatic mixed precision, AMP. Now the automatic mixed precision make things easier. So you can perform your training using FP16 within the framework. So you don't have to do all the manual job again. So the automatic mixed precision automates the process of training in mixed precision. It does the automation for you. It converts the matrix and the convolution into 16-bit for your tensor. So for example, what we have here, let's say this is our training layer, the convolution layer that you can see here. So the training is being done using what automatic mixed precision, which is both FP32 and FP16 as well. And the computation that will go within the FP16 will be run on the tensor core. And for example, this is an example here that you have your deep neural network here, the DL, the frameworks are here, and the under the framework you is embedded with, enabled with automatic mixed precision here. So which will be handled by the tensor core. So automatic mixed precision use. So how do we use the automatic mixed precision? We can use it using our frameworks through scripting. So it exists here in MX, MXNet, PyTorch also. You can use it on TensorFlow as well. And then you can use container. But however, in the container, I must say for TensorFlow, you can use, it's only possible with TensorFlow version 1. That is only where you can use the automatic mixed precision. If you want to use mixed precision, automatic mixed precision with TensorFlow version 2, it might not be possible. I've tried it. There are so many errors that you might envisage from there. Also, you can use PyTorch, also MXNet as well. So all of these, you can pull them on the NVIDIA NGC. So if you go to NVIDIA NGC here, so from here, so this is TensorFlow. Let me come to catalog here. Okay. Yeah, so you can search. You can search for TensorFlow, or you search for PyTorch. So if you search all of that, I'm coming. Okay. All right. So yeah, here they are. Yeah, you can just click. You search for them. You can see this is TensorFlow. This is PyTorch. If you click on them, you can get here. You pick. So you can pull. There are several versions here again. You can pull from there. But if you need to use, if you are using these are TensorFlow version 2. So here you can only use mixed precision. You cannot use automatic mixed precision. For you to use automatic mixed precision, so you click on the tag here. You come here. There is a version. There is version 19 here. Version. Let's go to 1907. So yes, if you pull this one, this is version, you will pull this. So you just need to click here, then you pull, and you cannot use that for your automatic mix precision.